OK, hi. So my name is Matei. I'm a grad student at UC Berkeley and also a Hadoop committer. I've been working with Hadoop for about 4 years now on various projects. And I'm going to talk about Spark, which is a new system we're building for high-performance, iterative, and interactive data analytics. So Spark is part of a bigger research project at Berkeley called Mesos. And the core idea in Mesos is that MapReduce and Hadoop are only the first step in big data analytics. So in particular, if you look at companies like Google and Microsoft and so on, we've seen a wide variety of new programming models for clusters being proposed after MapReduce. So Google alone has talked about 3 or 4 others. They include Parallel, which is a specialized system for graph processing, Dremel, which is for low latency analytics, and Percolator, the new web indexing system, which is very different from MapReduce. To enable this kind of innovation, all these frameworks are good at different things, and we'd like to have support for the same kinds of things in the open source software world. To really enable these to exist, we need a way to allow organizations to very easily deploy new frameworks and share a cluster, share physical resources and data between them, and also to make it easier to just develop new ones. So the Mesos project aims to provide that. It's a common runtime layer over which you can run Hadoop, you can run things like MPI, and you can run new frameworks that you develop, such as Spark. Spark is the first thing we've developed on top of it as an example. Mesos has a lot of cool features that I'm not going to go into all of them, but it's a highly optimized implementation that's scalable to tens of thousands of clients. It has a high availability using Zookeeper. It's able to tolerate failures of even multiple of the components at the same time. It's got strong resource isolation using Linux containers. It's been open source for about a year, and it's an Apache incubator project. Our biggest user of Mesos is actually Twitter, which has been using Mesos to run production jobs for about a year on over 100 machines. And they're using it especially for long-running services and stream processing. I encourage you to check out our poster at the poster session tonight if you want to hear more about Mesos. Back to Spark. So we had this system in place where we wanted to support these new programming models. We wanted to show one example of a programming model that's both useful and sort of straightforward to build to complement MapReduce on top of Mesos. So that's what we designed Spark for. And in particular, in Spark, we had 2 goals, 2 types of applications that we wanted to support that aren't handled efficiently by MapReduce and Hadoop today. These are, first of all, iterative algorithms, applications that just process the same data set over and over. And these are actually very common in big data analytics. A lot of machine learning algorithms are based on iterative optimization procedures, and a lot of graph algorithms like PageRank fall into the same boat. The other thing we wanted to support is very low latency interactive data mining. So you have all this big data sitting on the cluster, but queries with MapReduce and Hive and Pig take sort of tens of seconds, even for the smallest queries. And we wanted to enable sub-second latency. So that was the goal in terms of what we wanted to support. The other thing we wanted to do in Spark is to make it very easy to write jobs in this model. And to do that, we give you this programming interface in the Scala language, which is a Java-like language. It runs on the JVM, but it has some cool features that let you just write map and reduce as local functions and make the program much more concise. And for the interactive use case, we actually let you use Spark interactively from the Scala interpreter. So just to go into more detail about what we do and why the existing systems aren't this great for iterative and interactive analytics, a lot of the current systems, including MapReduce, are based on this programming model of acyclic data flow. So you have a graph of operators, and you have your data in a stable storage system like HDFS, and it passes through the operators, and it gets written out again to a stable storage system. This model is nice because it's simple, and actually it provides a lot of benefits in terms of what the runtime can do. So the benefits of this model are that the runtime knows the graph of dependencies and can automatically recover from failures. It can place tasks based on data locality and so forth, which is great. At the same time, though, the downside of this is that all these applications have to read data from stable storage every time and write it back out to stable storage at the end of each job. This is inefficient when your application actually uses the same data over and over. You have to do incur the cost of disk I/O or network I/O and deserialization every time. And both iterative and interactive data mining tools have this property of querying the same data set over and over. So in Spark, what we provide is a new programming model that extends the data flow model, and it's called resilient distributed datasets, or RDDs. The RDDs allow you to keep datasets of interest in memory across parallel operations, and therefore gain substantial speedups in applications that reuse the same dataset. At the same time, RDDs keep all the properties of data flow that made MapReduce attractive. So they have automatic fault tolerance, locality-aware scheduling, high scalability, and they also seem to be applicable to a very broad range of applications. So I'm going to start the talk by going into a bit more detail on the programming model, and then I'll tell you about some applications that various Spark users have built using the system. I'll talk a bit about the implementation, and I also want to try to do a demo of the interactive use case. So let's start with this. So again, the core concept in the programming model is these resilient distributed data sets, or RDDs. You can think of them as big parallel collections that are distributed across the cluster. And they have a few properties. So they're immutable, and this is one of the things that helps with fault recovery. And the way they're created is through these transformations that have a lot of the familiar data flow operations in there, things like map and filter and group by and reduce. And you start with a data in stable storage, you transform it, and you build an RDD. And the part where they're different from a lot of existing systems is you can tell the system that you'll reuse a data set over and over, and so it should cache it in memory. So this is part of it. The second thing you can do, once you've built these data sets, you have to run some queries on them and get some results back to your program. And we call these operations actions. These are things like count the numbers or add them up or even write them to an external storage system. Just to give you an example, here's something you can do interactively from the Scala console with Spark. In this example, we're going to, imagine you're an operator at a big internet company and some error is happening, and we want to interactively look through some logs that we have in HDFS. So we're going to load only the error messages from these log files into memory and then query them interactively. So what we're going to have here is a cluster with one node called the driver. That's sort of your master. It's where your shell is running, and a bunch of worker nodes that will run our tasks. And the first thing you'll type in is this one. You'll define lines as a text file in HDFS. And lines is a collection of strings, one for each line in the text file. And this is the base RDD that we're going to be transforming and operating on. Next, you can apply some transformations to it. So here we're applying the filter transformation to find the ones that start with error. And the syntax in red there is Scala syntax for a function, literal, or a closure. And one of the cool things about Scala is we can actually take this function and ship it to the cluster nodes and have it execute over there, because this function is actually a Java object that we can ship around. So that's what we do there. This is a transformed RDD. And then we may do more transformations on it. For example, we might say, they're tab-separated fields, and we'll want only field number 2, which is the actual message. So you can go ahead and do that. And finally, we'll tell the system to cache this. So it's not going to try to attempt to cache the whole log file. That might be very big, but maybe the error messages fit in memory, and we're going to keep those around. OK, so actually, at this point, one thing to note is nothing's actually happened on the cluster. So all these operations are lazy until you run an action. And then Spark will pipeline them and find an execution plan for them. So that's what we're going to do next. We're going to say, OK, let's see how many of these messages mention foo. Maybe that's the problem today. And we'll use count, which is an action. So when we do this, the master program is going to look at where the data is in HDFS, and it will send tasks to the worker nodes to process each block of the data, very similarly to MapReduce, and it will get back some results. The other thing that will happen, though, is that the workers will cache in memory any partitions of cached RDDs that they've built along the way. So now we have just the error messages on each node sitting in memory over there. So now we've got that. And after we run this first query, we can now run other queries significantly faster. So let's say maybe foo wasn't the problem. We'll look for bar. We can go ahead, and now the scheduler will look at where data is cached. It will hit the cache, and you'll get back your answer quite a bit faster. And of course, you can do more than just grep and count stuff. You can use a whole bunch of other operators as well. To give you a sense of what this means concretely in terms of performance, one of the tests we do is a full text search on Wikipedia on 20 extra large EC2 nodes. And Wikipedia is a 50 gigabyte data set. And with either Hadoop or just on-disk data and Spark, this full text search takes about 20 seconds. And if we load the data into memory, it goes down to less than 1 second. So that's kind of the performance difference between disk and memory that you can leverage using Spark. We've also scaled this up. So we've actually scaled up to 1 terabyte of data on 100 of the high memory machines on EC2. And there we can do full text search in about 5 seconds. And again, it's more than an order of magnitude faster than with disk-based tools. OK. The other cool thing about the programming model is that the way we do fault tolerance. So one option would be to do fault tolerance by trying to replicate the data in memory. This is also what you'd get if you tried to save the RDD in, say, an in-memory file system or key value store. But that incurs this cost of replication over the network, which is way slower than memory. So instead, we use a strategy called lineage, which is when we lose a partition, we remember how it was built from source data starting on disk to rebuild just that partition. So we represent each data set as this chain of transformations. And then if we were to lose, say here we lose node 3, we don't have to roll back the whole job to the beginning. We can just rebuild the partitions that were on node 3 in parallel on the other nodes. OK. Let me give you a second example of an iterative application this time. This is logistic regression. This is a common machine learning algorithm used for classification. So one example is you have spam and non-spam email messages that you've labeled, and you want to figure out, how should I classify these when I get a new message in the future. The idea here is you have these points. You represent each message as a point in some n-dimensional space. And you want to find a hyperplane or a line that best separates them. And a lot of these algorithms use an iterative optimization procedure. They start with a random line, like this one over here. And then they gradually improve it by evaluating this gradient function. So what they do is essentially a MapReduce operation. They add up a function from each point with respect to the current line that can be seen as each point sort of pushing the line in some direction. And then the line actually moves, and you keep doing this, and eventually you converge to a good separating plane. And the key thing to notice about this is all these iterations use the same raw data, which is the input points. They just apply a different map function on it each time. So keeping that data in memory can lead to substantial speedups. This is an implementation of logistic regression in Spark. And this is, again, just Scala code. So there's sort of two pieces to this. First thing we do is we define an RDD containing the points. So we might start with a text file and pass it through a function to convert them into Java objects. Maybe we have like a point class. And we'll cache those objects in memory. And the second thing, we have these iterations, and in each iteration, we do a map and a reduce. Actually, you don't need to know all the math here, but W here is the current separating line, and if you see, this function actually uses W, and when we pass the map function to the cluster, the value of W will also be shipped along with it automatically, and it'll just run over there and give you back a result. And then the underscore plus underscore is where we're adding up all the results. That's the syntax for that. So that's what the job looks like. And how, it looks nice. How does it perform? This is a graph with comparing the performance of this implementation against the Hadoop implementation. I think this is on about 30 gigabytes of data on 20 machines. And basically, what we see here is Hadoop has a constant cost for each iteration because it has to run a full MapReduce job, which reads the data from disk, deserializes it, does the math, and returns an answer. In Spark, the first iteration takes a little bit longer, but subsequent ones are quite a bit faster. They're actually about 20 times faster than Hadoop here. And this is because in this job, the cost of I/O and of deserialization actually dominates the running time of the job. And the math we're doing per point is quite a bit less expensive. And with Spark, we can just incur only that cost of the math and not have to repeatedly read this data set over and over. All right. The last thing, just to show you, even though one of the neatest things about Spark is the in-memory caching, you can also use it just to write plain MapReduce kind of stuff. You don't have to have everything in memory. So this is how you'd write word count. And basically here we use maps and reduce by key as a parallel reduce so that we can add up the counts for every word. This looks a lot like your MapReduce word count. All right. So let me just talk a little bit about what people are using Spark for. Spark is being used by a bunch of machine learning groups inside Berkeley and also at Conviva, which is a startup company that does video distribution and analytics. Just some examples of applications people have built. The Mobile Millennium Project runs a large-scale EM algorithm for inferring city traffic conditions based on GPS measurements from taxi cabs or from people running a cell phone app. And they've been using Spark to do that on about 160 nodes. Monarch is a system for finding spam on Twitter that's also been using Spark on the order of 100 to 200 nodes. I'm going to talk about in-memory analytics on Hive data. And then the last thing there, the ones at the bottom are some sort of simpler applications that we've also built. So I'm not going to show results for all of these things, but I did want to talk about this one, the Conviva one. So one of the jobs that Conviva does is after showing a live video, for example, like the Hockey Cup or whatever, to viewers, the customers that hosted that video that had the content want some analytics. And one of the jobs here is called the GeoReport, which will aggregate different metrics by city, by country, by the user's browser, all kinds of different groupings, and give you back a summary. And when they ran this as a bunch of Hive queries, this took about 20 hours for a week's worth of data, which is not too bad. But when they switched it over to using Spark, it only took about half an hour. So why do we have these speedups, even though this isn't really an iterative application or even an interactive one? The interesting thing here was when you write this as a bunch of Hive queries, there's a lot of common work done across the Hive queries that doesn't get reused. So just loading, loading the data from disk is part of it. A lot of these group bys are on the same data, so you could just keep it around in memory. Decompressing it, filtering it with your where clause, dropping the columns that you're not actually using in your query, but you had to decompress and load anyway, and so on. And in Spark, we could load the data only once and run all these queries substantially faster on it. Okay, and the last thing that's interesting about RDDs and that we've started to work on is we think as a programming model, it's actually pretty general. So I hope I've showed you can do MapReduce with it. We can also do a lot of the things you do with Microsoft's Dryad. So the runtime in Spark is a DAG of tasks. It's not just separate MapReduce jobs. So you can express more complicated DAGs. And another interesting thing we've built on top of it is Spragle, Google's graph processing framework, which at first looks very different from MapReduce, but it turns out you can implement it using these. And this project is called Bagel, for Berkeley Bagel. And the last thing that we're doing is SQL implementation. We're trying to port Hive to run on top of Spark. This is still in progress, and we don't have a great name for it yet. OK. Yeah, OK. Let me just talk a little bit about the implementation now. So as I said, Spark runs on top of Mesos. This means you can use it to share resources with Hadoop, current versions of Hadoop, as well as MPI and other applications that you can run on top of Mesos. It can actually support any Hadoop input format or output format. So even though it's not a modified version of Hadoop or something like that, it's a separate code base, but you can use your data that's inside Hadoop or HBase or other systems. And also, there's no changes required to Scala. So this means we didn't have to hack the compiler to be able to do this. It's about 10,000 lines of code overall. A little bit about the runtime. As I said, the actual runtime is DAG scheduler, looks similar to Microsoft's Dryad, but it has additional support for knowing where data is cached in memory and reusing that, as well as it's aware of the partitioning of data sets. So it can avoid shuffles when you have two data sets that are hash partitioned in the same way. And the final thing, the interactive Spark, this is a modified version of the Scala interpreter. This is actually maybe the most technically involved component, where we have to make sure that whenever you type in a line of code, we ship any necessary classes that you've created to the rest of the nodes on the cluster, and we run the lines of code over there. So we had to make a bunch of changes to the interpreter to do this. But the good news is that once you have it, you can use the system interactively. All right, so in the rest of the talk, I want to actually try to show you a demo of this. So I'm going to switch over to Firefox. Hopefully, you can see what looks like Firefox over there. And usually, I do this at a terminal. So this is the first time I'm trying to use this web-based terminal, just because to be able to do it on the conference laptop over here. So we'll see how that works. But hopefully, it will work well enough to get an idea. Yeah, so I hope you can see the text. Let me know if it is too small or something like that. OK, so I've set up a cluster here on EC2 with 20 extra large machines and HDFS and this 50 gigabyte Wikipedia data set. And I'm just going to go into this. And here we have the Scala interpreter, the Spark interpreter that we're running. So this looks a lot like the Scala interpreter, except it says Spark at the top. And you can do your standard Scala stuff in here, like add numbers and things like that. The other thing you can do, which is new, is you have this variable SC called the Spark context. And this is what you use for running stuff on the cluster. So what we're going to do is we're going to define a data set that represents the Wikipedia file and query it interactively. And I have the URL of the file as an environment variable, I think. Oops, sorry. Equals system. Yeah, OK, there it is. Sorry, I'm not super used to this keyboard. OK. And we're going to have here a file, which is the wiki file. So this is an RDD of strings, 1 per line. This is a tab-separated file. Let's take a look at what the records in it look like. So I'm going to ask for just the first record. So this is the first line in the file. And these are records that have basically 5 tab-separated fields. They have an article ID, title. This happened to be the first thing in this dump. Date modified, an XML version, and you can't see the fifth field, but it's a plain text version of the article. So what we're going to do in this demo, we're only going to use the title and the plain text. So let's define a class that represents that. And you can just create a Scala class. So that's how you do it. That's an article. And now we're going to map this data set to extract only these two fields from it. So bear with me for this one. So we're going to take each record and split it by tabs. OK. And it turns out some of them don't have that fifth plain text field because they're things like images. So we're going to filter it to get only the ones with exactly 5 fields. And then we're going to map, we have these arrays of tab-separated fields. We're going to map each one to a new article. And we're going to take field 1, which is the title, and field 4. OK. So this is an RDD of articles. Again, this is lazy. Nothing's happened on the cluster. So let's try now to actually look for something in it. Sorry. Oops. I'm just going to count the ones that contain Berkeley. So we're running this on the cluster now. And this will take a little bit, because this is just working with on-disk data now. But let's see how it does. So this is running over here. It's running 362 tasks, and you can see a bunch of them are finishing. And there we go. So there's 13,000 of these articles, but the query took about 20 seconds. So that's not exactly interactive. So what we're going to do next is cache these articles. We're going to tell the system, OK, cache them. And now when we run the query, the first time we run the query, it's going to take about the same time as before. Oh, it doesn't like me doing that. OK. Yeah. So let's do that. First time we run it, nothing's in the cache. So it's going to take the same time. But it's going to remember that it's cached these partitions of the data set on the nodes. So that's what it's printing out right here. So it's going ahead and doing that. Yeah. OK, and again, took about 20 seconds. And the answer is the same. Let's try it again now with the in-memory data. Yeah, and when we run that, as I said, it's less than a second. And the data is in memory. You can now ask any question you want. And I'm running low on time, but I'm going to ask the natural question here. Yeah, and it's less. Stanford's only 11,000. So if there's one thing you remember from my talk, it should be that. So thanks for listening. Spark is open source. You can find it at the URLs out there. And we'd love to talk to you if you want to use it. Thanks.
Are you taking questions?
Yeah.
Oh.
I think so. I hope so.
So this works well when you want to dedicate the memory to a particular problem set. But in a multi-tenant environment where you're doing lots of different jobs, how is that going to be coordinated? Yeah,
that's a good question. So right now, you can use the resource sharing controls in Mesos to control how much memory each user has. Another thing we want to do in the future is to allow users to share memory for some data sets. But that's not implemented yet. So basically, with Mesos, you can isolate the memory across users. Yeah.
Thanks.
Yeah, other questions?
So when you direct to cache a data set, what happens if the data set is too big to fit into memory?
Yeah, so if the data set doesn't fit in memory, we can cache it on disk. And you get performance that's in between. It sort of degrades gracefully. So it's not going to be worse than if it was only on disk to begin with. But it might get better. Yeah.
Right. Thank you.
Other questions?
So related to Rumping's question, how do you know if you have enough memory? I mean,
yeah.
It's hard to track in Java. So
right. That's a good question. So actually, this is one of the more like technically sort of funky things we had to do is how do you estimate memory in Java? And we have a few strategies for it based on reflection, essentially. To be able to, like, you're caching 1 million objects, we're going to look at 100 of them, see how big they are using an estimate based on reflection. And it works reasonably well. If that doesn't work, we also want to let the user provide hints about that. Yeah. Are there questions?
I have a question. This seems to work really well if you have immutable data sets.
Right.
So for instance, for graph processing, if you have an infrastructure like Bagel, and you're mutating the graph repeatedly, would you see the same kind of benefits from the
So yeah, the way we do the graph processing, even though each data set is immutable, you can create a new version of it at the next step. So that's how you can emulate mutable state. It's the same thing happens with functional programming. So think of the immutable ones as maybe versions of what's logically the same data set. Yeah.